Okay. Hi everyone. Um, Welcome to the class. Let me remind you that there is another set of problems due next week on basically authentication. So don't forget to spend some time on that. Okay, but we move on to the new topic. So basically, in the whole first part of the class, I mean, one part of it, one aim of this was to show a basic of cryptographic thinking of how do we model what a security is, how do we argue about security of some construction based on security of another, like a security of a PRF in terms of PRG, security of a MAC in terms of PRF, security of encryption, and on, right? How different security notions can be, right? Like that they're sensitive to, is this one time? Is it many times? Is it passive attacks or is it active attacks? And we've seen that these definitions, these notions very much matter because something that passes a one-time security has attacks against if you do many. Something that is passively secure and completely standard has attacks when you up the ante and attacks are active. So it's quite a rich story, right? But it's the theme that was driving us was applications, and the theme that is it's sort of the pinnacle of this, if you will, is that we both get an encryption and authentication and active attack security, but it's all in the setting where two players pre-share a symmetric key, right? And now they can use it to encrypt, they can use it to authenticate. In some sense, we have worked out that space. The public key cryptography starts with the question, how do you distribute keys? How do you create the same key material on the two sides? So Alice and Bob have the same 128-bit key, 160-bit key, 256, whatever it is, AES, triple DES, whatnot. But how do they start this? And if you remember the PRG story, right? Once you have shared entropy that is at least security parameter long, you can expand it to any number. You can create MAC keys, encryption keys in both directions, in one direction, however many you want. Because at that point, all the symmetric key cryptography kicks in, and there's basically no limits to how many keys you want to create. But you have to start with this at least security parameter long. If you have constant number of random bits, that's searchable in constant time. So you have to, but we have no idea how we create them up to now. How do we get Alice and Bob to create this? So that's the basic. So let's look at the key exchange problem, okay? And without public key cryptography, excuse me, you can solve it using trusted third parties, and that's how systems were engineered early on. It was called Kerberos, or a single sign-on, and was basically something called key distribution service, and that's how it works. So in any organization, on any network, right, you have n folks, And if they need to communicate securely, then they need in total n square keys, and it's not clear how they initialize them. So if everyone authenticates trusted third party, this is a term in cryptography or security, TTP, a trusted third party. If everyone authenticates to this trust TTP, and they have just a single shared key, namely with this TTP. So Alice has a key KA, and TTP also has KA, and TTP, Alice associates KA with TTP, TTP associates KA with Alice. And everybody in the system has a key like this. That's the only key they have. So that's nice. It's scalable for users, less so for the TTP. And now if Alice and Bob want to secretly communicate, they can do so with the TTP help. How so? So Alice says to TTP that she wants to talk to Bob, and Bob, Alice can max this with KA, right? So Bob knows that it's coming from Alice. Okay, TTP has KA. So you can verify this. So it's not only secure, it's also authenticated channels, pairwise channel that every user has with its TTP. TTP encrypts under KA, basically a ticket that says, the ticket's content is A and B's name concatenated, and a key, symmetric key that they should be using. But in addition, Alice gets a ticket that is an encryption under Bob's key, KB, of things that looks basically the same that Alice have gotten. Why does TTP use, how does TTP form this? Okay, this is chosen fresh every time. So this is a fresh key that TTP chose. KB, TTP knows. A and B are identities that are part of the Alice request, and TTP, without loss of generality, tags all these entities in the system with a pair like A, which is an identity of Alice, however, whatever identities are in the context, comma a key. Okay. In the versions of this, which was Kerberos, the encryption here was just CPA secure, and it was malleable. And you can see that this is not like the best way of using this stuff. And indeed, it will have attacks because it was CPA secure only. In particular, it was malleable. You can see from this design, what is the point of writing AB here? Well, the supposed point of this was that if Alice received it, she would decrypt the string and she would know that this key is safe, or at least TTP says so, for her to use with identity with Bob's, with whatever Bob identity is. And this assumes that these people have some notion of shared identity space, so they know what an A and what a B corresponds to. Perhaps corresponds to a user, like a username, perhaps an IP address, perhaps a domain name. That's context dependent. So encrypting the stuff was supposed to basically authenticate it, so that Bob, who gets this ticket and when he decrypts it, he knows that this key is safe to use for talking to Alice, which is just a plain text encrypted here. But CPA schemes are not non-malleable, they're very often malleable, right? So somebody can take this ticket and basically rewrite the identity here and switch the fact that this was a key given to A and B replace the A with a C and say, okay, this key should be used with a C. Okay, they still didn't get the key, so perhaps this is safe. I mean, this is a useless attack because the attacker doesn't know this key. But stuff like that is a dangerous thing. So these malleability attacks were utilized to fool Kerberos tickets, so that you end up, some service, let's say B, ends up talking to you and end up performing, stuff for a different account and a different entity than was intended. So Alice can decrypt it and get the key. She forwards the tickets. Bob gets the key, and now they have this the pairwise established key, right? So minus the fact that this was buggy because of CPA security, what this once we have CCA secure encryption and possibly authentication as well, basically authenticated encryption, what this does is that it establishes a fresh key material for both parties. Okay, what's the problem? So as far as you have active passive attacks are involved, by CPC security, nothing inside here is known. So you can replace this encryption of the key material with an encryption of random stuff, and nobody can tell. And therefore, this key is completely protected, and it's as good as if it just randomly, by magic, appeared here, right? Because as far as passive adversaries are concerned, transmission of the stuff can be replaced with the transmission of an encryption of an all-zero string. And once you do that, then this stuff appears here completely by magic. So it is a secure key exchange. It does accomplish magic appearance of a completely random string and no information about it to computationally limited adversary, right? So no information in the sense of not through information bounds of Shannon, but in terms of indistinguishability to polynomial time attackers. Okay, so this is a Kerberos key distribution system, and basically, of course, it has this bottleneck, a trusted TTP, right? And TTP is just basically we would have to authenticate to a single party and establish channels with that party. So it's a bottleneck, but it's also a security vulnerability, right? Like there is somebody out there who knows everyone's keys. Okay, so how would you generate without it? And the thing is that there is a way. Let's see. First thing is first solution. It's like kind of a half solution was given by Merkle, and it's interesting to see first. And the real solution, in some sense, was given by Diffie-Hellman with Diffie and Martin Hellman. Their paper was called "New Directions in Cryptography," a seminal paper. And then soon followed reverse Shamir-Adelman RSA. Because if you squint your eyes, Diffie-Hellman key agreement, or indeed any key agreement which is non-interactive, minimally interactive, is a public key encryption. And RSA was another one. And the story didn't quite end, so we have other notions of even more complex encryption schemes that, for example, identity-based encryption, where you don't need people's public keys. You just need their identities, and that suffices to encrypt for them. There is more complex notions of encryptions. Functional encryption is that you can encrypt and only people who have basically solution to some function will be able to decrypt it. I could add a fully homomorphic encryption to the list, and that wouldn't exhaust this list either, where I can encrypt, and many people can encrypt under a given public public key, and then some party who doesn't have the decryption key can compute on the ciphertext of this encryption any algorithm. So how do you encrypt on ciphertext? The result is the encryption of the output of the intended algorithm on the clear texts. So the algorithm proceeds from encryptions to encryptions. The person who operates this doesn't know anything. They just know that if the input encryptions encrypted inputs, then the output encryptions encrypt outputs, but they don't know either inputs or outputs. They go from ciphertext to ciphertext, but the correctness is preserved. The algorithm is being applied to the inputs. So the encryption has this property. This allows non-interactive secure computation. I can send you my encrypted inputs, like my encrypted DNA string. You can use your machine learning model on my encrypted string. The result is the output of the model on the string encrypted. So my proximity to some bad genes, or my probability of whatever, some outcome of some treatment, etc. And all of this gets encrypted, and only that can be decrypted in the last step. Okay, but this so this is incredibly rich stuff that can be built on top of this. We will start from the beginning. And in this class, we will, basically, essentially stop here. Okay, and we go into some of these things in an advanced class or in seminars. Okay. So basic key exchange by Merkle. What's the problem of the key exchange? So let Alice and Bob be connected by a network. It is a public network. So there is an eavesdropper who can intercept everything. But we want security only to eavesdropper. So he will not tamper with it. He will not send the messages on his own or modify the ones that are transmitted, but he will hear everything. In such a setting, is it possible for Alice and Bob to create a shared secret key? So Alice and Bob, after this exchange, create a key K that eavesdropper should learn no information about, at least in this usual sense we have now of computational indistinguishability from a uniform random string, right? Even though the eavesdropper has been witness to all their communications. So Merkle asked the question: can this be accomplished with symmetric key primitives, with encryptions, MACs, PRFs, PRPs, PRGs? And the answer is yes, kind of. Okay. So the answer is something called Merkle puzzle, and it is a viable solution, but it is pretty inefficient. And let's see what I mean. It's sort of not exponential time either, but you will see in a sec what I mean. So let's define a notion of a puzzle. This notion actually has many uses in crypto, not just for a Merkle puzzle. Take a symmetric cipher, let's say AES, with 128-bit keys. That's a cipher E. And let a puzzle indexed with input P be a cipher using the P as a key of some fixed plaintext, let's say message. Okay. And moreover, the key is not truly uniform. In fact, 3/4 of key bits are fixed, they're just zeros. And only 1/4 of the bits here are truly random. So the 32 bits at the end. Now, if I give you the puzzle is an output of this cipher. So it is a ciphertext, an output of the cipher E. If I give you this cipher, the ciphertext, the solution that I ask you to get back is the input P. But of course, the input P, the 96 bits of it are known, right? So it's really just this part that is interesting. Okay, what is happening here? Well, in what sense is this a new object? First of all, treat E as an ideal cipher. So it's a stronger modeling tool that we have used already several times. So, which means that for every key, not just randomly distributed, this E is it behaves like a random permutation. I need this because I'm fixing 96 bits of the key. So the real keys here occupy a completely insignificant fraction of the whole domain of keys. So an arbitrary block cipher could behave horribly on those keys, but an ideal cipher will not. This is something called a medium hard function, because if the solution to this, you can solve it in a 2 to the 32 attempts, right? Because you can cycle over all these possibilities, run the cipher forward on input message, and just test whether it hits the ciphertext I gave you or not. Okay, so you can always do this. This is of course flexible parameter, right? So I can make this into 34 bits, and this becomes to the 34. I can smaller it. I can make it fewer, right? I can only do 20 bits. So this is completely flexible. There's tons of other. This is an example of a mechanism where, if let's say I give you the puzzle, I'm not going to talk to you unless you solve it. That if you really want to talk to me, that forces you to, on average, make 2 to the 32 or maybe 2 to the 31, okay, on average, right? Because with some probability you get lucky. So it then forces you a slowdown. Where was this thing would be useful? For example, these are, I'm blanking now on the word, but these are, it's not a cookie, some other word. So in a communication system, right, like a TLS, is a TCP server is being bombarded, possibly with denial of service, TCP open requests. So it gets smarter and it says, okay, I will start a TCP session, but only if you solve this puzzle. A standard equipment would at this point need to be forced into performing 2 to the 30 AES. It's annoying. Oh, okay, so it will be smaller. It will be only 20 bits. So let's say 2 to the 20 AES. So it's 1 million. It takes a bit. Perhaps it takes a second to do that. So it creates a slowdown in starting. The client has to slow down. The service, not so much, because in order to create this, it just had to pick this at random and do 1 AES. Why would the service do it? To prevent automatic, massive denial of service attacks, because now, the denial of service attacks work by like massively bombarding this poor GCP server with millions of requests in order to force the guy into, wasting memory and computing power, creating TCP sessions. The attacker now has to do 2 to the 20 AESs per each, and this will not be economical. Okay, the payoff is too small. Okay, I blank what the name of this mechanism is, but maybe one of you will know and write it on the chat. Will probably come back to me. Okay, why would I do this? Okay, using such puzzles, here is the Merkle protocol. Alice prepares 2 to the 32 of these puzzles. In other words, she chooses 2 to the 32 of these random PIs. Of course, there's going to be collisions because each of them is just 32-bit long, but that's okay. And then so she chooses 2 to the 32 real long keys and something we will call nonces. Okay, and she creates a puzzle as before, encrypting under this kind of 3/4 zero keys. But now the inside of the puzzle is no longer a fixed message. It's a message that has some fixed elements, like PUZZLE, but then has 2 variable elements. One is the nonce, the other is the key. Okay, somebody says CAPTCHA, but no. So CAPTCHA is a test for a presence of a human. Okay, it is not something that is designed to slow down an automatic engine, right? Like just a processor. This is designed to slow down a processor. Like you just have to perform to the 20 AES things. It's still, you might not be human. In fact, you're not gonna be human, right? Because a human cannot do, to the 20 AESs. So yeah, but it is in the same family of sort of tricks, right? Like I know, but it's just that we want to slow. The purpose is different. You want to slow down a processor rather than make sure that there is a human there. Another within that actually, range. There's another thing that maybe you do. Maybe it's not enough to force a processor to slow down. Maybe you also want to insist that whoever talks to you kind of wastes certain amount of space, of memory on talking to you. So speed and memory, processing and memory are 2 different resources, and a lot of computation stuff is optimized to just optimize computation. So sometimes forcing people to compute more is an arms race, but they can win it. I mean, not win, but have an edge on you. But if you force them to use memory, then it actually scales worse for the attacker. Okay. The same mechanisms, by the way, are absolutely key in blockchain stuff, right? Where we basically identify an entity with computational power and therefore have possibility of an edge against an attackers if the sum of the computational power of good participants is within some good fraction of the sum of the computational power is simply greater sum of computational power of attackers, then these type of mechanisms allow people with the majority of computational power to have an edge over all attackers, unless the attackers have a total computational power that trumps everybody who is honestly participating in the system, then I'm not sure that there is a possibility of security. And in some blockchain architectures, people are changing this. I mean, there's other forms of these type of balances, but one is replace computational power with memory. So sort of use the mechanisms that enforce certain memory contribution from both honest guys, from anybody who participates, and therefore, and maybe this will create a more just and defensible mechanism. Of course, in blockchains, another thing, as you can see, this is an arms race that so wastes everybody's cycles, right? Because everybody is now forced to perform these like insane number of AES cycles, only so that to enforce this parity, well, everybody will overheat and contribute to wastage of energy, wastage of your resources, and fossil fuels, etc. So these mechanisms have another dimension, which is like, can you do it without basically Earth self-destructing? Okay, let's go back to these puzzles. So the puzzle now will have a fixed element and then a nonce and a key. And Alice sends 2 to the 32 of such puzzles to Bob. Bob picks a random one and solves it. Because he finds in 2 to the 32 time the PI on a random ith puzzle that he chose, how can he test? He decrypts, and he tests whether the decrypted stuff looks like puzzle followed by anything, right? And the only one that does with overwhelming probability is going to be the correct one, if it is an ideal cipher. So, by the way, this cannot be just a single cipher, right? Because now how many bits are here? It's 256 plus a bit, plus some. So you have to construct like a larger cipher in some sense from this, but okay, we've seen that you can, right? And we already argued that, for example, 2-block CBC is a PRF. It's a oh no, that was for a Mac case, right? We argued that it's a 2-block CBC Mac is a Mac, or rather, that was an optional problem in a homework. It is an optional problem in the homework because that's the still outstanding homework actually. Okay, so a little bit different than what we need here, but related. Choose and you know what, if you just do a counter electronic codebook mode, that's fine too. So just think of this as 3-block ciphers. This is first block, this is the second block, this is the third block, all encrypted under the same key. It will be okay. It's not exactly one-time encryption. You do 3 things, but the probability something goes wrong with an ideal cipher is basically the same as the probability that xi, ki, and this stuff collides, and that probability is 2 to the minus 128. Okay, so he chooses a random one, he solves this, and he sends the nonce to Alice, and he uses the corresponding key as the shared secret. Alice gets back the nonce. She created all of this stuff, so she has a table translating xi's to ki's. So when she gets certain xj, she knows what the corresponding kj is, and in fact, she could compute ki's from xi's using a PRF, so she doesn't even have to keep a table. She just recomputes the same PRF on input xj. Why is this secure? In what sense is this secure? So what did the adversary see? He sees all these puzzles, which are encryptions of xi ki pairs, and he gets one of the xi's back. So first of all, how much Alice have worked? She created 2 to the 32 of these puzzles. N is 2 to the 32. To create one, it's easy. It's a single block cipher, or 3 in the implementation before, right? So it takes this much time. How much Bob worked? He solved one of these, so it took him this much time, but he solved only one, randomly chosen. Now, what about eavesdropper? Well, eavesdropper's work is quadratic, because if it's an ideal cipher, this stuff has no information, and the only way to find any information within it is to search through the preimages and apply the function forward, if it is an ideal cipher. Yeah. So okay, or finish this to the 32, find the 32 bits that remain in the key, apply it to decrypt, and recognize that it says that the message is of this form, at which point you learn one xi-ki pair. So you can solve these at random, choose them randomly, and hope that you chose correctly. If you want to be sure that you do it, you have to spend 2 to the 64 time, solve them all, 2 to the 32, each of them solved in this time, you're gonna get here. Of course, you can work only in a fraction of this time. And basically, if you work fraction, if you want, instead of doing it for sure, you want just probability epsilon that you do it, then you will work with time epsilon times 2 to the 64, right? But if you want to reduce it significantly, say to 2 to the 54, then you will have only 1 in 1,000 fraction the chance that you break it. Still, the problem with the system is that it has a very high cost, right? So especially bandwidth is costly. So whereas 2 to the 32 local operations, perhaps it's okay, it's not blazing fast, but it's feasible. Bandwidth like this, 4 billion ciphertext, is it's something you would like to avoid if you have to encounter such a bandwidth just to establish a key between a client and a website, or one cell phone and another, or a cell phone and a base station. And all you got out of this is some edge over the bad guy, but it's not a great edge. In particular, this quantity is not exponential in this. It's only quadratic. So you might remember this introductory exercise that will sort of guide you into so that you kind of see why we state all security properties in terms of negligible advantage and polynomial time adversaries. If the advantage is merely quadratic, this does not scale well. And basically, indeed, like if you want to make this 2 to the 80, we'd have this make 2 to the 40. It was hardly viable as it was. Increasing this would make it into something, completely impossible. Well, but very often in algorithms, you have this situation. Okay, so somebody came up with this basic algorithm, and it had kind of a quadratic gain. Okay, so instead of working like this, I worked with square root of time, and I kept, in order to keep at bay adversary that has this many resources, I needed to work in square root of time of the adversary. Can I improve this so that I somehow rearrange this, or I repeat this, or I combine this in some other way, so that the work of the good guys is, say, cube root of the bad guy. Okay, because this shows some non-trivial improvement between the work that the bad guy is forced to do and the good guys are doing. And nobody could figure out any such amplification of Merkle puzzle algorithm. And indeed, basically, Impagliazzo and Rudic showed that in some sense, this is the best you can do. So you cannot get a better gap between bad guys' work and good guys' work than quadratic using symmetric cryptography at all. And lower bound, so this is an example of a lower bound in that it's a lower bound as in you cannot do faster than this. So you cannot accomplish this fending off adversary with a given computational power any faster than working with time square root of that power. And lower bounds in computer science are very hard and kind of unusual, to show that you can do in certain time. Okay, this is positive examples, right? Algorithms. But how can you show that you cannot beat certain times, that there is no sorting algorithm that is faster than n log n, that there is no search possible, right? The extreme case of this is that P and NP are different, that there is no polynomial time algorithms to solve problems that are NP complete, right? Like satisfiability, graph isomorphism, not NP complete, but graph colorability, right? Like many other forms of NP complete NP complete problems. So we don't have a proof that polynomial time algorithms cannot do them. So in what sense is a proof here? So the proof it's a conditional, that if there existed such a construction that beats this, and if the proof of security for this construction was in some sense a black box, which means that it is a form of a reduction from security of this construction to security of the symmetric key building blocks. That if such a construction existed, then something would some believed hypotheses in complexity theory would be falsified. So it's conditional in several layers of conditions piled upon conditions, and yet that's the best type of negative results we see in cryptography. These are so-called separation results. So they say there is a gap between key agreement and symmetric key cryptography. Everything in the symmetric key cryptography was linked, and in some sense, the most a domino that makes all the other falls is collision resistant hash function. If you want to start a little later than that, then you just one-way function basically creates PRG, PRF, PRP, max, encryptions, all the rest, right? But can it create key agreement? And Imperator just stated no, it can't, right? So that's a separation, as in some problems are harder than others, and there cannot exist, there is no efficient construction that in some way is black box, so with an accompanying argument of certain form, but these are the forms of arguments that we know of, no others, so so it is a negative result. Okay, so what do we go from here? Is that we need different assumptions. Like we have to have a new building block new building blocks in order to create key agreement and public key cryptography in general. And Diffie-Hellman proposed such a building block. Okay, so the problem is, okay, as we already know, and can there be an exponential gap between how much of this needs to work and how long the good guys compute? So here is a, excuse me, a little still informal view of a Diffie-Hellman key exchange protocol. We will make it more formal soon. So, but we need to like sort of review modular arithmetics, and so that will take some time. But let's take a first approximation. So take a large prime, like a 200-bit long prime, fix an element which in this range, it's a residue mod P that generates a large enough subgroup modulo P. This notation ZP star refers to all the set of prime residues mod P. So actually this will end with P minus 1. Sorry, it's a typo. Which are coprime with P. And you know, if P is simply, well, actually, so if P is prime, then all the residues here are coprime with P, right? Because P is a prime, so it's coprime with everything. Okay. Now, what I mean by subgroup, a group, multiplicative group, is formed by, I will be talking about the multiplication modulo P. If you take any element in here and multiply the modulo P, you're going to create an element here. Modulo P, you always fit into this range, except maybe you hit a 0, but you cannot hit a 0 because there is no 0 here to begin with. The only way to create a 0 would be to create an element that is multiple of P. But you cannot do that if P has no prime factors. Okay, so multiplications will basically, that means that it's, oh, okay. There is another element of what this means for this to be a group. It's also that there are inverses in here. So any element here has some other one such that if you multiply them mod P, you get a unity. That's less trivial, and you sort of don't know at first why that is, but you will see soon that that is the case. Moreover, this group for all primes or many primes, I think actually all primes, is cyclic. It means the following. There is some elements here which are called generators. if you take such an element, let's say 2, and you look at different powers of it modulo p. So 2 squared, 2 cubed, to the 4th, to the 5th. At first, they're just integers. Modulus does not work, does not do anything to them because it's such a long modulus. But soon enough, exponentiation makes this longer and longer, right, the number. So it will hit 200-bit limit. At this point, modular reduction is going to put it somewhere back into the set. And when you multiply by the base, let's call this base, this 2, let's call it a base. When you multiply a base, your modular reduction, and you're going to hit some other element. So a multiplication by a base jumps you from element to element in the group. It's a Fermat's theorem that if you do it p minus 1 times to any element here, you're going to get a unity. So any element here multiplied p minus 1 times by itself always gives you a 1. Except some elements can, that's for sure true. Every time you multiply something p minus 1 times by itself, it gets you a 1. But some of these things, you multiply them much fewer times, any factor of p minus 1, and you already get a 1. For example, p minus 1, if you multiply that by itself, that's like taking a square of minus 1, which is a 1. So therefore, it's going to be here. You can check that p minus 1 squared modulo p is actually a 1. So if p minus 1 has large prime factors, then many of these elements here will have the cycles that they generate will be as long as these factors. And there will be some elements here which will generate the whole group, meaning that they will actually, the size of the cyclic group will be p minus 1. That's what's meant here. Okay, and now what do we do with this element G that has this property? Alice, so prime P and this element G is part of the public description of is part of the setting for Diffie-Hellman. Everybody knows what the prime is and what the generator is. Generator is not random, it's fixed. Everybody can also check that it is a generator of the group. There's nothing secret about this. Factorization of p minus 1 can be published, and everybody can verify what these factors are, and even can run primality testing algorithms, which are efficient to verify for yourself that these are primes, that p is prime, and all the given factors of p minus 1 are indeed primes. And so you can test that G is a generator. Okay. What do you do with this? Alice picks a random exponent, little a, in this range. This is exactly the size of the subgroup generated by G. And what she does is she sends G to the power, little a, modulo p. So as I said, if G is a generator, then, okay, that's another thing. So we'll see this actually. If G is a generator, that means that it takes p minus 1 times, you need to take G to the p minus 1 to hit a unity. Before, it's not a unity. That also means that this function, as a function of little a, is a one-to-one function. These powers will never collide for two different exponents, a and a prime, in this range. Because if they did, then you divide them and you get a unity, which would just mean that contradict the fact that the cycle is supposed to only happen at p minus 1. So this operation basically creates, the capital A is a random element in the set if the little g is a generator of this. Bob does the same. He takes a random exponent b and he generates a random element in this group by taking the base to the exponent little b. And so it's a modular exponentiation. the key that they will create is g to the power that is a product of these two exponents, so a times b. Okay, you can compute this product. So how long is this number? It has 2000 bits. This has 2000 bits. The product, you can do this faster, but you know, even if you do it by the books, it has 4000 bits. Okay, so you exponentiate. Exponentiation, modular exponentiation is we will see this in a next time, but it is a polynomial time algorithm, so it takes time linear in the number of bits here. Okay, but how is this computed? Where? So by the homomorphic properties of exponentiation, if Alice takes this integer and takes it to the power little a mod p, the capital B is g to the b mod p. But if you're doing operations mod p, you don't have to do this operation in the middle. You can postpone modular reductions to the very end, and nothing will change except of efficiency of computation. So this result is equal to this integer mod p. This integer is g to the b times a. So it is this one. And Bob can do this as well, taking this part that Alice sent, basically taking Alice's message and exponentiating it to his exponent, which also resolves into an integer mod p, an integer which is equal mod p to g to the a times b, right? So they can officially, so how long Alice had to compute? She needed to perform one exponentiation mod p and a second one. And so did Bob, right? With two times he had to exponentiate something to his random exponent little b. Once here, the second time here. Okay, so 2 modular exponentiations. That's what it cost. Is it secure? Well, this is what an eavesdropper sees. He knows the prime modulus, he knows the generator, he can even get the factorization of p-1, so he verifies that this is a prime, this is a generator indeed. Then he sees 2 values, g to the a and g to the b, both mod p. And the question is, can the attacker, eavesdropper Eve, compute this g to the ab? Diffie-Hellman, in a sense, defines a function. So the key that they compute is a deterministic function of the transcript. Because if little g is a generator, that means that this exponentiation function is a one-to-one function. It has no collisions, meaning if capital A, the value of the exponentiation, is published, there exists a unique pre-image, little a, that makes this equation true. This little a is called a discrete logarithm between base g and capital A value. Likewise, the little b is also a discrete logarithm of base g of this capital B. So given all these p, g, capital A, capital B, the little a and little b are well defined, and therefore this value is well defined. So that's the Diffie-Hellman function of the inputs, which is basically the parameters and the transcript, and the key. And the whole thing is, how hard is this function to compute? First of all, in what sense? Well, the following sense. I fix the parameters, and my experiment is, I'm a challenger and you are the attacker. I publish these primes. I mean, we both can agree on these primes. Okay, it's like we're just choosing them. You can even, you as the attacker, can choose a prime and a generator. But I choose a random element, both of these elements at random, which basically means I choose a random element in the domain of the function, because the function, the domain of it was pairs of elements in the group. What's the group? The group is the multiplicative group modulo p. Okay, so from 1 to p minus 1, they form a multiplicative group mod p. Okay, that's the group. So you're getting two elements randomly sampled from the group, or a random element in the domain, which is a pair of group elements. And I'm giving you the value of the function on this random argument. Hold on a second. I think I have to disconnect the phone here. Oh, no. Yes. Sorry about that. So I choose a random argument and I give you the function, the value of the function on this random argument. And I ask you, you have to give me the value. This is not exactly the same as a one-way function, because in the one-way function, the experiment is that I pick an argument and x, and I give you f of x. And I ask you y equal f of x. And I ask you, you have to invert the function. You have to give me the x such that, which is the preimage. Here it's different. I give you the random argument, and I ask you to evaluate this function on the random argument. Diffie-Hellman assumption is that that this function is hard, meaning that no polynomial time attacker can, with better than negligible probability, compute this function on random arguments given by the challenger. And that is exactly what is needed in this protocol, right? Parameters are fixed. Even they can be fixed by, the NIST or NSA. They can be adversarial. It's still okay. I choose random argument from the domain. That's a random transcript of a Diffie-Hellman key exchange. The attacker, given this x, has to compute the Diffie-Hellman function on this argument x. X is a comma b, and has to solve the function on this. The Diffie-Hellman assumption is that there is no polynomial time adversary algorithm which would compute values of this function in this experiment, where it has to solve it on random inputs given by the challenger, with probability more than negligible. So that was the Diffie-Hellman assumption. I mean, that they basically hypothesized it. And why did they hypothesize such a thing? Because here is one way that you could break this. If the transcript is revealed, right? So the argument to the function is revealed. you could break it if you could compute discrete logarithms base little g modulo p, because given the capital A part, if you could compute discrete logarithm, you would get this value. That's precisely the discrete logarithm between g and capital A. And knowing the little a, you would compute this, right? Because that's what Alice does. She takes capital B and exponentiates it to little a, and she gets this. You could also compute this discrete logarithm. You would also be computing this key that way. So if discrete, and of course, the basis of this algorithm is that discrete logarithm modulo large primes appears hard. We don't know general algorithms. We know algorithms for some subsets of primes with some very, very special properties, but we don't know this problem in general. And it's easy to generate primes that avoid these properties and for which there's no known discrete logarithm attacks. So that's the basis for the Diffie-Hellman assumption. The two assumptions are sadly not known to be equivalent. So we don't have a reduction that shows that the only way to compute this from these two is through computing discrete logarithm. The status of this problem is sort of unknown because for some class of primes, these closeness between hardness of discrete log and hardness of Diffie-Hellman they're very close. There are reductions which are surprising between these two problems, but it only works for some classes of primes for now. Okay. And there's other group structures like elliptic curves for which you can define the same two problems where over elliptic curves, these are different groups. They're not like I take an integer and I just multiply it over and over by itself modulo prime. There's some other underlying arithmetic operation, but nevertheless it defines a group of a cyclical nature, so cyclic group. And so I have the same arithmetic possible. I take an element and I apply, because if I have a product relation, then I have an exponentiation, right? Because exponentiation is defined by the product, by just applying the product as many times to its right to the base as this exponent gives. So if I have multiplicative group, that defines exponentiation, and that defines an instance of the Diffie-Hellman protocol for that multiplicative group. So you can instantiate it in elliptic curves as well. And then you will have the same discrete logarithm versus Diffie-Hellman assumption. And the same question whether the algebraic structure of that particular group allows you to relate the two problems closely. So there is no known exactly equivalence between the two. And yet, I think all attacks on Diffie-Hellman work by solving discrete logarithm. So there is no faster attacks known. And these attacks on discrete logarithm depend on the group. So in modular residue groups, there is attacks that work in time exponential in the cube root of security parameter, which is of the length of the prime. Such attacks are not known over elliptic curves. So elliptic curve attacks are weaker than this, and that's why there's a movement towards elliptic curves in one. There's one of the motivations. This algorithm is called general number field sieve that achieves this. And if you, so look, if the attack is 2 to the square root of n, third root of n. If, let's say, I want security like 2 to the 80, so I want my security parameter to basically tell me the lower bound of attacks is 2 to the security parameter. Okay, so that's the common reading, intuitive reading of what a security parameter is in a crypto system. So let's say I have a security parameter k, so I want the best attack to be 2 to the k. That means that k has to be roughly around, so I'm ignoring constants and other lower order terms. This is by the way O tilde, which means that there are some lower order, not just constants, but some other lower order, some logarithmic terms in here. But let's just ignore them for now and basically say that, you know, this is approximately this much in exact terms, in which case the exponent here would have to be approximately third root of n. N is the length of this prime, bit length of this prime. So that means that n is like a cube power of security parameter, right? Because of constants here, if I want 80 parameter, what would be cube power, right? It would be, I don't know, 512 with 3 zeros. So what is that? 500,000. Thankfully, I don't have a 500,000 long modulus, but that's because of the lower order and constants in here. Because if I increase the security parameter by what is it, like 50%, so therefore k grows by 50%, so 3 over 2, in how big do you expect n to be? How much bigger? 3/2 to the cube, 1.5 to the cube, right? Which is like 4 or something. Well, I did not get just as big of the jump, but almost, right? So again, the lower order terms have modified this somewhat. So 3 is less than 1.5 cube, but almost. If you jump here twice, the estimates on the running time of this algorithm basically means that now the length has to hike up. What is it? From 3 to 15, it's 5. So that's closer to 1.5 cube. Okay, this jump. Sorry. So this, you know, what do you expect here? To be 2 to the cube, right? Because you just grew the security parameter by, so k grew by a factor of 2. So you would expect n to grow by a factor of 8. It didn't. It grew by a factor of 5. Again, these lower order terms, you know, tampered this growth, but you still had a big growth. This is not great, because even when I said that the exponentiation time of modular exponentiation is polynomial in the length, I actually said that it's linear in the length. Well, yes, exponentiation, I don't know, maybe you have seen it, but there's fast exponentiation algorithm and others, square and multiplied, that are linear in the length of exponent. But the underlying, so they're linear, they do perform linear what? Linear modular multiplications. The time of multiplication also grows with the exponent, with the modulus size. In fact, you know, a sort of a trivial implementation of multiplication would grow quadratically in the right, because you might remember the elementary school arithmetics. If you were writing long numbers, and they would be rather long, you have 600 digits, so you cannot fit them in any constant size objects like integer, long, right? These are 16 bits or 32 bits, but not 600 bits. So you have a sequence of 32-bit longs that represents this, and both little a and little b, of p, right? So, and if you are multiplying two objects here, modulo p, that will again take time. That is, okay, so the trivial algorithm will cross multiply each of them, which will be quadratic in the length. So there is a faster multiplication algorithm, Montgomery multiplication. It's beautiful that you can speed this up. It doesn't have to be quadratic. It's length to the 1.7. Very nice algorithm, very beautiful observations that speeds up multiplication of long numbers. Still, it's 1.7. So the cost of these operations will grow like n, the length of prime, to the power 2.7. There is 1 power of n because it's linear number of moles, linear in the length of exponent. And there is 1.7 because of this cost of modular multiplication itself. So this is your n, but the running time of the implementations that use this n, length of prime, grow like this to the power 2.7. So 5 factor of increase in bandwidth means 5 to the power 2.7 increase in computational time. Anyway, it is it doesn't scale that great. And for elliptic curve groups, there is no known corresponding number field algorithms. So at least for now, elliptic curves are more resistant. And the size of elliptic curve groups is just twice the security parameter. So the number, which basically translates into description of elliptic curve elements, and there's also some moduli that define an elliptic curve. These moduli will be 160-bit long only. If for 2 to the 80 security, 256-bit long for 2 to the 128-bit security, etc. You might notice a very simple relation. The sizes of these groups are twice the security parameter. They're not sizes of groups, they're sizes of group descriptions. The sizes of the group itself is 2 to the power of this, right? So that's not a coincidence. We'll see that discrete logarithm in any group has a lower bound. It cannot be stronger than this. So if you basically, there's a generic discrete logarithm algorithm that given a group the size solves it in time 2 to the 80, which is a square root of the size of the group. So if there's 2 to the 160 elements in the group, you take a square root of that, you get 2 to the 80. And these generic algorithms are lower bounds on how big you need the group to handle a certain to achieve a certain security parameter. But this growth is at least linear together with the security parameter, right? And so even though elliptic curve operations are more complex, arithmetically you have to implement a bunch of modular moles and divisions and modular reductions and so forth. On the other hand, because you're working with much smaller moduli, even though the basic atomic operation that creates a group multiplication is more complex, in the end the implementation of it are going to win, and they're already winning. Okay, so therefore there is a movement to adopting elliptic curve crypto. Oh yes, and I have like some old slide which shows that when you do so you will open up SSL connection. At the time it was called TLS, transport layer security, with Google. It told you that the encryption here, the key agreement was well. So RC4 is a block cipher. SHA is the hash, and its SHA-1 is phased out. So this is quite an old slide, and so is RC4 actually. And this refers to the key agreement, which used elliptic curve Diffie-Hellman, and also that was the key agreement, but it was authenticated by RSA signatures, which we'll look at later. For now, key agreement for us is not authenticated. We assume passive adversary, so we don't worry about making sure that I'm talking to the right person and not an adversary who interferes. I'm only want to accomplish, for now, passive security, that the two of us establish a shared key that a passive attacker cannot get any useful information about. So that's an instance of elliptic curve. So it's the same Diffie-Hellman, but with elliptic curve group operations. Okay, I think this is a good place to stop. And if you have some questions or comments, please let me know. Speak up. Okay. There is a lot of modular arithmetic material that will be used in this segment of the class. If you have any time left from anything, I have guideline on the syllabus for refreshing the modular arithmetics, learning about it. Please go ahead, because we'll be using it heavily right now. Okay, and happy Thanksgiving, everyone. Take care. Write on Piazza if you have questions on the homework exercises, and pipe in if you let me not just be the only one who tries to give some hints. If you have some idea, then please help your fellow students. Okay, take care, everyone.